Well, let's continue. This is the basic logic of ANOVA. It's very important. You must notice that. And here, this is how can we divided the variation into different parts. So the first one is the total variation. We call it total SS. SS is the sum of square. And we can use SST to represent total variation. And how to calculate the total variation? This is the formula. It's sigma bracket x minus x bar square. And let's go back to this slide. This is our example. So how can we figure out the SST, the total variation? So that is x minus x bar square. And notice that S here, x means each number in either group. So each original number in either group. And here x bar. Notice that this x bar is not x bar for each group. It's x bar of all the original numbers. So here that x bar means this one, 2.2. So this is the x bar when we put all the numbers into a single group, and we can get the x bar from the 12 original numbers. So here SST should be the first number 5 minus x bar 2.2 square plus the second number 3 minus 2.2 square plus the third number 1 minus 2.2 square plus the fourth number 2 minus 2.2 square and plus till to the last number 1 minus 2.2 square. So SST is the summation of all of these numbers. So I have mentioned that the calculation is too difficult. There are only 15 numbers in this question. If we have more than 15, for example, we have 70, 72. So you need to do a lot of calculation. That's very difficult. Okay, so this is how can we get SST. And the basic logic of ANOVA is actually partitioning the total variation into two parts. So the total variation is SST. So that is the total variation. And what are the two parts? The first part can represent the effect of the treatment. So that means that this part is the variance among different groups. So it's the error caused by different groups. So this part abbreviated as SS between. That means it's the variation between or among different groups. So we can use SSB to represent this part. And here SSB, this is the formula for SSB. Sigma Ni times x bar I minus x bar square. So what's the meaning of that? This one, Ni, that means This Ni means the sample size in each group. So that means the group I, the sample size of group I, and X bar I, that is the X bar for group I. And this one X bar is the same with last formula. It's also the total average of all the original numbers. Okay, so let's go back to this slide. Here we want to calculate the SS between. It equals to the first group is corresponding sample size is 5 times its X bar I 3.6 minus X bar 2.2 square plus the second group sample size 5 times is X bar 2 minus 2.2 square and plus 5 times 1 minus 2.2 square. That's all. We have 3 groups, so we sum 3 numbers up. So that is SSB. That means the variation among different groups. So this part can represent the effect of different groups, of different treatment. But please notice that therapy A and therapy B, there may be some variations between these 2 groups. But this group is not completely caused by the different groups therapies, because the random error also be included in this part, because we find that these are 2 samples, sample A and sample B. Samples are randomly drawn from the population. So if we draw a sample from the population, there will be random error. So SSB can represent the variation between different treatment together with a little part of random errors. And the last part in the partitioning, the total SS. The last part is error, or we can call it within groups. So that means variation within a single group, is abbreviated SS within. So we use SSW to represent this part. So this part can represent the effect which is completely from the random error. So this part we can find, this part can be calculated by using this formula. X means each individual number, each original number. X bar I is the same with this one. That means the mean of each group. Okay, so let's go back to this slide. Now we want to calculate the SS within groups. So we start from the group 1. Its corresponding SSW is the first number 5 minus its corresponding X bar for the first group 3.6 square, and the second number 2 minus 3.6 square times plus and plus till to the final, to the last number 2 minus 3.6 square, and then plus the second group. The first number is 3 minus its corresponding x bar within the group. 2 plus the second number 3 minus 2 square plus till to the final, to the last number, and then plus the three groups, the group 3. The first number is 1 minus its x bar 1 plus the second number 0 minus 1 square plus to the final 1 minus 1 square. So this is how can we get SSW. Okay, so here we say that we divided the total variation into two parts, SSB and SSW. So in mathematics, we can find there will be a special relationship between these three parts. So what is the relationship? The relationship is this formula. This formula is very, very important. Actually, in chapter 10, you don't need to remember this formula for how to calculate some part in ANOVA. You don't need to know how to calculate the numbers, but this formula, that is the relationship between these three parts of the variation, that is very important. You must notice that. You must remember it. So SST equals to SSB plus SSW. In mathematics, we will prove that, not in this class. Okay, so here, let's calculate all the numbers by using a computer. We find that SST equals to 34.4, SSB equals to 17.2, SSW equals to 17.2. Oh, we find that SSB and SSW, they are the same, but most oftenly they will not be the same. Okay, so here the relationship between SSB and SSW, that is not very important, but the relationship between these three parts are very important. So you can find that SSB plus SSW equals to SST. So it's our provement for the relationship between these three parts. And here is the partitioning of the SS of the variation. In ANOVA, another important thing is partitioning of DF, of degree of freedom. So that means the variation should be divided into different parts, as well as DF of freedom. So here, the total DF, we already use nu T to represent the total DF. The total DF is the same formula with what we learned before. That is the n minus 1. But please notice that this n, this capital N, means all the numbers in the question. So here in this question, we have 15 numbers, 15 individuals. It doesn't matter a special number belongs to which group. We just want to know how many individuals in all of the three groups. So that is n. That is the total number of individuals in this study. So total DF is equal to n minus 1. And This part can be divided into two parts too. The first one is treatment df. The treatment df equals to k minus 1. So here k means number of treatments or groups. For example, in this question, we can find that we have 3 therapies. So that means we have 3 treatments or 3 groups. So k equals to 3. And the last part is error df. That means the random error. And error df equals to n minus k. N is the same with the first column and k is the same. That means number of treatments. Okay, so the relationship between these 3 parts are total df equals to treatment df plus error df. Because we found that total df is n minus 1. Treatment df is k minus 1. And error df is n minus k. So we'll find that the summation of the last 2 parts equals to the first part. So that is the relationship. Okay, so in this question, we can figure out all the df. We have 15 individuals in this question, so the total df is 14. We have 3 groups, 3 therapies, so the treatment df is 3 minus 1 is 2. And error df is n minus k, that is 15 minus 3 is 12. And we can find that total df equals to treatment df plus error df. So here, this is very important. This is very important. You need to remember how to calculate the df for the 3 parts, because the calculation of this part is very easy. It's easier than the calculation of the SS. So we don't want you to remember the calculation of the SS, but you need to remember the calculation of df and the relationship of the 3 parts of df, as well as the relationship between 3 parts of variation. Okay, so that is the partitioning of df and variation. And the next one, let's learn how to get the test statistic in ANOVA. We said that the test statistic in ANOVA is F value. But how can we get F value? Here, we need an indirect measures. We need an indirect value. We call it mean square, abbreviated MS. Mean square, MS. When a sum of squares is divided by its number of degrees of freedom, the result is called a mean square. So actually, the mean square is SS divided by df. So here we can calculate 2 MS. The first one is treatment MS. We use MSB to represent the treatment MS. It's equal to treatment SS, SSB, over treatment DF. Treatment DF equals to K minus 1, right? And the second MS is error MS. It's equal to error SS over error SS is actually SS within groups. We can use SSW to represent this part over error df. Error df is n minus k. So notice that the total variation has no MS. So we don't need to calculate the total MS. We just have two MS, treatment MS and error MS. Okay, so now we can get the test statistic, the F value. The F value is the ratio of MSB over MSW. So please notice that the ratio must be this one, MSB over MSW. So you cannot change it. So F equals to MSB over MSW, and MSB equals to SSB over its corresponding DF of freedom. MSW equals to SSW over its corresponding degree of freedom. So the null hypothesis will be rejected only when the variation due to the treatment effect greatly exceeds the variation due to random error. We said that SSB, that is the variation among different groups, and we said that this part can be caused by the variation of different groups and the random variation, the random error. So the variation in this part actually includes two parts. That is the variation between different groups. And random error. But we said that in the denominator, this part SSW, this variation is only caused by random error. So we use this part divided by random error. So let's suppose if there is no any difference between different groups, that means the variation of different groups equals to 0. So this ratio should be very, very close to 1. Right? So that means if F is close to 1, that means there is no difference. There is no difference between the groups. But if this part, the variation among different groups is not equal to 0, so we know that this is variation. We use sum of square to represent the variation. So this part must be more than 0, and its ratio should be more than 1. Right? So if we find that F is far away from 1 and is more than 1, that means there will be difference among groups. So this is the meaning of F value, and we can compare F with 1 to make the decision. But please notice that according to the sampling error, even when there is no difference among groups, F cannot be completely equal to 1. But F value should be near to 1. So in ANOVA, we need to compare the F value, what we calculated with the data given in the question, with the standard F value. So we also need to find the standard F value from a special table, that is F table. Okay, so let's summarize the basic logic of ANOVA. The results from the analysis of variance are normally displayed in the following table. So we can find that this is the source of variation. And we said that there are three parts of the variation in ANOVA. The first one is the total variation. We use SST to represent this part. And it can be divided into two parts. The first one is treatment or among groups variation. We use SSB to represent this part. And the third one is random error or within groups variation, denoted SSW. Its corresponding DF is very important for you to remember. The total DF is n-1. The treatment DF is k-1. K is the number of groups. And error DF is n-k. And here is the mean square MS. MS equals to variation over its DF. And here for the random error is the same as SSW over n-k. And this part F is the test statistic. F equals to MSB over MSW. But please notice that F you cannot use MSW over MSB. That's not correct. So you cannot change it. So it must be equal to MSB over MSW. For example, in this question of 3 therapies, we calculate the result by using computers. And here, this is the SS. We have seen it before. This is the DF. So here, you can calculate with this data. You can calculate the MS and its corresponding F. For example, for the treatment is MS equals to SS divided by its corresponding DF equals to 8.6. And for the random error, it's the same. SS divided by its corresponding DF equals to 1.43. And next one, we need to calculate the F. The F value. The F value should be treatment MSB over MSW equals to 6. Okay, so this is the F value, what we calculated with the data given in the question. And the next one, we need to compare it with the standard T value. And I will explain that later. Here, this table is very, very important. In our examination, sometimes I will give you some long answer questions about calculation in ANOVA. For example, I will show you this table. I will give you some important numbers in the table, and then I will give you the informations about the study. For example, how many individuals are included in this study, how many treatments are used in this study, and you need to figure out the other numbers in this table. For example, if I told you there are 61 individuals in this study, so you can know the total DF should be 60. If I told you there are 5 groups, and then you can know the treatment DF should be 4. And if you have calculated these two numbers, you will know what's the results of this blank. That is 56, right? Because we said that the total df equals to treatment df plus error df, right? And then you can figure out the MS and the F value. If I give you the standard F value, you need to make the decision, reject H0 or not reject H0. In this table, you can figure it out, right? Yes, it's the difference of total and SSB. Okay, so that is very important table. Actually, you need to remember the relationship of SS and the relationship of DF, and how to calculate MS and the F value. Okay, next one, I will explain how to find the standard F value and how to get the P value from the ANOVA table. Here, we need to use a new appendix table, that is table A7, critical values for F distribution. We can find a standard F value used for ANOVA test in this table. Okay, so now let's turn our page to 159. This is the table A7. Okay, it's here, 159. This is table A7. And how can we use this table? Let's look at this one. In the first column is the df in the denominator. And in the first row is the f in the numerator. So here, let's go back to our table. This part. We have mentioned that for the f value, it was the ratio of MSB with MSW. So, which one is the numerator? Which one is the denominator? Yes, this one is the numerator. This one is the denominator. So in that table, the F in the numerator actually means the F of treatment. This is 2. And the F in the denominator should be error df as new within, right? It's 12. Okay. So let's go back to the table. We need to find 2 in the first row, the F in the numerator, and we need to find 12 in the denominator. Let's find it. 12. Okay, it's here. So in its cross position, we can find 2 numbers. Right? These 2 numbers, 3.89 and 6.93. We can get these two numbers. And which one should be used in our ANOVA? Let's go back to the title of the table. Here is a notice. We can find that upper means P equals to 0.05. Lower means P equals to 0.01. So, do you understand now? We have 2 numbers, and the notice tell us that the upper one is used for when alpha equals to 0.05, not the lower one. So we just use the upper one, the upper number. That is okay. Okay, so here the standard f value should be 3.89. So we can write it as f nu 1 and nu 2, comma nu 2. Let's write it here. We can write it like this one. We can find that f and in the right corner alpha and comma bracket. There will be two numbers in the bracket. The first one is the df in the numerator, that is 2. And the second one is the f in the denominator, that is 12. It's equal to 3.89. Is that right? Let's go back to the table. Yes, 3.89. Okay, it's here. It's here. So this is the standard f value. And the rest of things we need to do is to compare the f value we calculated in the question with the standard f value. Okay, we find that we calculated and get the number of 6. 6 is bigger than 3.89. It's bigger than the standard value. So that means its corresponding p is less than alpha. So you can find that it's similar with what happened in the other methods of hypothesis test. Okay, so when p is less than 0.05, we need to reject H0. So now let's summarize the procedure of the hypothesis test in ANOVA. Step 1, H0 is mu1 equals to mu2 equals to mu3, and HA is at least one mean difference. Alpha is still 0.05, and we just need to we don't need to write down all the procedure of calculation for each numbers. We just list this ANOVA table. We list all the numbers we need in the table. And here is the test statistic f equals to 6. And we compare this number with the standard number. And we found that p is less than alpha. So we decide to reject H0. And then the conclusion is there is significantly difference among the three groups. So that means there is at least one group is different from the other groups. Okay, so this is the procedure for hypothesis test of ANOVA. Okay, but here is another question. We found that there is significant difference among the three groups. So that means at least one group is different from the others. But which one is different from the others? We need to do some further analysis. So here, the further analysis, we call it multiple comparisons. So this part is not very important. And I will introduce this part to you, and you can understand it. The multiple comparisons is used for compare each two groups and identify which one is different from the others. So here in this question, we find that the three groups are different. So we need to compare each two groups in a time. So we need to do 3 times of hypothesis test. A versus B, A versus C, and B versus C. But here's some questions. The first one, if in the ANOVA we found that P is bigger than 0.05, so we cannot reject H0. And then, do we need multiple comparisons? Of course, no. We don't need to do that, right? Because if P is bigger than alpha, we don't reject H0. That means there is no difference among the 3 groups. They are the same. So if they are the same, we don't need to do the multiple comparisons because A equals to B equals to C, right? So that means the multiple comparisons is only used for P less than 0.05. That means this method, multiple comparisons, is only used when we reject H0 in ANOVA. And next one, can we do the above mentioned comparisons by using t-test? Of course not. I explained the reason, right? Because if we use 3 times of t-test, we will increase the error, right? So we need some special methods. There are so many methods for multiple comparisons. And here I will introduce you the student's Newman-Coles multiple range test. We call it SNK method or Q-test. That's a very simple method for multiple comparisons. This is the test statistic. That is Q value, and this is the formula for Q. Here, MSE. MSE is actually MS error. So do you remember how to calculate the MS error? It's here, MS error. So we just put this number into the formula and then we can get the Q value. So here I won't show you how to calculate the Q value. I show you the results directly. Here we compare A and B and we get its Q, and we found that its probability P is bigger than 0.05. So what's the meaning of that? We identify the difference between A and B, and we found P is bigger than alpha. So that means A and B, they are the same. There is no difference between A and B. So mu A equals to mu B. And next one, we compare A and C. We found that the P is less than alpha. So that means A and B is different. They are different, right? Mu A is not equal to mu C. And the third time, B versus C. P is more than 0.05. So that means mu B equals to mu C. So what's the meaning of that? According to the 3 conclusions, we will find that mu A and mu C, they are different, right? But mu B is in the center. So we will find that these parts are the same, these parts are the same, but mu A and mu C, they are different. Okay, so that is the multiple comparisons. Okay, so this is the method of ANOVA. Next one, let's do some exercise. Here is exercise 1. You can read it by yourself. Okay, so here we will find that there are 4 groups for treatments in this question. And here we cannot use t-test because the number of groups is more than 2, so we need to use ANOVA. So here, the first question is write down the hypothesis for the test. Okay, so we can know the hypothesis should be H0 is mu1 equals to mu2 equals to mu3 equals to mu4 because we have 4 treatments, right? And alternative is at least one mean differs. Okay, so that is the hypothesis. And number 2, fill in the blank. So the first part, this one, this is easy to calculate, right? The total minus SSB. And how about the F? Let's go back to the data. Here we find that we have 16. The total number is 16 and divided into 4 groups. So here, the total DF is 16 minus 1, right? 15. And the DF for treatment should be 3, 4 minus 1, right? And the error, the DF of error is 12. And MS equals to SS divided its corresponding DF, right? And we said that MS total has no MS. And finally, F equals to MSB over MSW. And if we calculate the F, we can compare it with the standard F value. And then we can get the answer. Okay, so can we reject or not reject? We find that the F value is bigger than the standard one, so that means P is less than alpha, so we can reject, right? We can reject the null hypothesis. So the conclusion is the liver versus body proportion are different among the 4 groups, right? Yes. Okay, so that's all for today's class. See you next time.